The other type of reactions that we can do starting with alkynes are addition reactions. Remember that for an addition reaction, we need a pi system, and in the case of triple bonds, we have two pi systems. So if you treat the two pi systems as individual pi systems, they are just like a reaction of an alkene, a double bond, for additions, right? So it's exactly the same mechanisms and the exact same reactions that we saw in the chapter of alkenes. So really nothing that new in this new chapter. So we have two pi bonds that when react with either HCl or Cl2 or Br2, we will add those two atoms across the double bond. Now, if we use a second equivalent of it, then we will add two more of those atoms across the second pi system, across the second double bond. And that's how we form 4 pi bonds in the final molecule. So starting with the triple bond that has a sigma bond and 2 pi bonds, we end up with the 4 new sigma bonds formed. Just as in the case of double bonds, acetylene or any triple bond has the electron density here in the center where the pi bonds are, because that's where the electrons are, and those are ready to go and react. There are 4 main types of addition reactions of alkynes. We're just going to see the mechanism for 2 of them, and those are the ones that we already saw for in the chapter of double bonds of alkenes. And so that those are hydrohalogenation and halogenation. You must be aware that there are other reactions that can be done. The hydration and the hydroboration oxidation, those mechanisms are a little bit more complicated, and you may see them in organic chemistry too. As for now, you just have to know that these reactions can be done, and that starting from a triple bond, you can get a ketone, or you can get an aldehyde based using these reagents, and you must use them to do the homework and to do the practice. But be aware that I'm not going to ask you about these 2 during the exam. Okay, so just be aware that you may have to use them during the practice, because there are some exercises that require you to use them. But it's just a simple reaction. You don't have to know the mechanism. You start from a triple bond. By using these conditions, you get a ketone. You start from a triple bond. By using these conditions, you get this aldehyde, this terminal carbonyl. So again, you're going to be asked about these in the exam. You're not going to be asked about these in the exam, but you must know that they exist, and you may have to use them for some of the homework. So let's talk about the hydrohalogenation. It's very similar to what we saw for double bonds. So here we start with a triple bond, and first, by using one equivalent of HX, we add those to the double bonds, to the double bond, yes, and then we get the other double bond, and we add another set, and that's how we end up with the geminal dihalide. Here we have one example. We start with a triple bond, H and Cl added across the double bond, well, the triple bond, right? And then another equivalent gets added. How come that the 2 Cl's end up on the same position, on the same carbon? The reason for that is because Markovnikov rule still applies. And we're going to see the mechanism, and you're going to understand why the 2 Cl's end up in the same position. The same happens for HBr. So here we have the Br first going to the more substituted side, and when the second molecule of HBr gets added, the second Br also ends up in the more substituted carbon. We're going to talk about it later. So here it is, the mechanism. So remember, the first step is going to be my nucleophile. Here is where the electron density is, where the electrostatic potential is. The triple bond attacks the H and the Br leaves because the Br is a good leaving group, and the H could be added to both sides of the triple bond, right? It could go here or it could go here. Remember that if it goes here, like you can see right here, it forms the most stable carbocation because that's the most substituted carbocation. Now, Br will come and attack, and we will get this vinyl bromide in where the Br is in the more substituted position. Now, when a second molecule of HBr reacts, we have a double bond that will attack the H, and the Br will leave again. So it's the same reaction happening twice. And remember that we could get that H in two different positions. We could have it here or we could have it here. If it ends up here, like we're seeing in this molecule right here, we get the more stable carbocation because it's the more substituted carbocation. Now, when the Br attacks, the two Brs end up in the same place, right? So Markovnikov rule still applies in the case of triple bonds. So you see here, what we're doing is we're comparing the rate of the reaction. The electrophilic addition, this first step, is lower in the case of alkynes than in the case of alkenes. And the reason for that is because of this sp hybridized carbon that it's lower to react than this one right here. This carbocation is more stable, right? So that's why this one is going to form faster. This one right here is not so stable, and so that carbocation is going to take longer to form. But again, let's review the steps. Electron density, that's my nucleophile, attacking the H, and the Br leaves. Now I form the more stable carbocation. Remember that the H could end up here or here. But if the H ends up here, we will get here a primary carbocation, and that's not a good one. Now the Br is going to come and form this Markovnikov product. Now this happens a second time, and so we have the double bond attacking the H, and then the Br leaves. We form the more stable carbocation and not more stable carbocation. You see here we have the triple bond, and here we have, sorry, not the triple bond, the tertiary carbocation, and here we have the primary carbocation. Primary carbocations are very unstable, so that's why we will form the tertiary carbocation, right? So this is not formed. The H ends up here in the terminal position, so we can get that tertiary carbocation that now can come and get attacked by the Br. And so just a reminder that because of the lone pair on the Br can delocalize, right? These are the two resonance structures for that intermediate for that carbocation. And this is the hybrid structure. That positive charge is delocalized between these two atoms, right? It's delocalized between the Br and the carbon. And so that's why the carbocation is stabilized by the resonance given by the Br. And so here we have another example, but in this case, it's not hydrohalogenation. In this case, it's halogenation of the alkenes. And the exact same rules apply that the ones that we saw for double bonds. We will go through that bromonium ion or halonium ion, right? It's often that we see it with chlorine and Br. And so the mechanism is just the same one as the one that we saw for double bonds. So here we will get a halogen across each one of the carbons on the double bond, and then when a second molecule of that Cl2 or Br2 reacts, then we will get another set attached to the second pi bond. So here we have an example with a Cl. We get two Cls first. When the second molecule reacts, we get the other set of Cls, right? And remember that this one can be drawn like this, but it can also be drawn like this. This molecule is not chiral because none of the carbons are connected to 4 different groups. And so let's look at the mechanism. The first one is the formation of that halonium ion. In this case, it's the chloronium ion. This is very, very unstable because of the ring constraint, right? It's a 3-member ring, and on top of it, we have sp2 hybridized carbons right here, so that's very constrained. So that Cl that left in the first step now can come back and attack from the opposite side. Remember this from the previous chapter. And so we get the 2 Cls across the double bond. That reaction happens again with a second equivalent of Cl2. So again, we form that halonium ion, and the Cl that left in the first step now can come and attack from the opposite side. And so that's how we get the tetrahalide, right? We get 4 chlorines across the triple bond.